time to last week. All right, so let m be greater than or equal to 2, and consider an m by n grid of unit squares. Such grids will contain many rectangles whose vertices are points on the grid and whose edges are lines from it. For example, a 2 by 2 rectangular grid contains exactly 3 non-congruent rectangles as shown below. Find all m by n grids that contain exactly 100 non-congruent rectangles. So let's consider an arbitrary rectangle of size m by n. Big that, just imagine the grids as like the lines. Now let's consider what the congruent rectangles are. The congruent rectangles are essentially just the rectangles with the same side lengths, right? So for example, this is congruent to this, right? These are both 1 by 1 rectangles. This thing here is congruent to this. These are both 1 by 2. Even though the order is swapped, this is a 2 by 1, this is a 1 by 2. They're both congruent. So first thing we want to eliminate is having the same congruent rectangle, same orientation, but in different spots. So to do that, we're only going to consider rectangles that are tethered to this edge, right? They have one corner here. So then it remains to just consider the side lengths. Now, in this case, I have what m is 5 and n is 10, right? So I have like a square here, and everything after this is greater than m. So within this part, I can have these rectangles that have multiple orientations. So I can have a 2 by 1 here, or a 1 by 2 like this, right? So in order to count the non-congruent rectangles, I have to account for this, right? So when we look at the case where, let's look at A, B, or A by B rectangles, right, within n by m. When B is between, or when B is strictly less than or equal to m, that means when it lies in this part here, we have to be clever about how many ways in which we can count. So what we're going to do is we're going to write A, and for each B, for each B, we're only going to count the rectangles with, so B is my height here, right? We're only going to count the rectangles with width less than B. So that's going to take care of the orientation, because I'm never going to end up with something that's wider than it's long. So for each B, count rectangles with width less than or equal to B. So this gives us B rectangles, right? B rectangles. And adding this up over all the B's less than or equal to m, this gives us exactly half times m plus 1, right? This is just sequences in series adding B from 1 to m. Now we consider the case where B is strictly greater than m, but less than or equal to m. So that's in this case, right? That's in this area. So here, when we have a rectangle here, like this, we're never going to be able to change the orientation this way, since this lies outside the rectangle. So we don't actually have to worry about the orientation. So now for each B in this domain, we have M rectangles. M rectangles. So that gives you M times, and how many are there here? There's N minus M things here. So it's M times N minus M possibilities here. So the total number of non-congruent rectangles in a M by N grid is half M times M plus 1 plus M N minus M. And we want this to equal to 100, right? We want this to equal to 100, and we're going to find some restrictions on M and N. So let's just factorize out the half and the M. So we have M plus 1 plus 2N minus 2M equals 100. This gives us M times 2N minus M plus 1 equals 200. So obviously now we just have to look at the factors of 200, right? That'll give us our pairs M and 2N minus M plus 1, which will determine N completely. But one more thing we will notice to slim our process down even further is that if M is even, well, then we have 2N minus M is also even, plus 1 is odd. So we have even and odd. If M is odd, then we have 2N minus M becomes odd, but then plus 1 becomes even. So we're going to have odd and even. So we only need to look for the factors of 200 such that 1 is even and 1 is odd. So what are the possible factors? We have 1, 200. 2 and 100, that doesn't work, right? Because those are both even. 3 is not divisible. 4 and 50, again, doesn't work because those are both even. 5 and 40. This works. 6, 7 doesn't. 8 and 25. Again, this is two pairs. 1 is even, 1 is odd. 10 and 20 doesn't work. Yeah, so this is all our pairs, right? Because we don't want to have, since M is strictly less than N, or since M is less than or equal to N, 2N minus M plus 1 is always going to be greater than M, right? So we only need to list out these pairs. We don't need to list out the opposite pairs, 25, 8, 45, 201, right? Because we need M to be the smaller number anyways. Another thing we needed was that M is greater than or equal to 2. So that rules out this pair. So we only have these possible pairs. So we have M equals 5, 2N minus 5 plus 1 equals 40, which gives us that N is equal to 22. So we've got and this one we have M is 8 and 2N minus 8 plus 1 equals 25. So this leads us to N is equal to 16. So our two possible pairs are 5 by 22 and 8 by 16. Any questions or comments? If not, then I'll hand it over to Michael because you had something to say, I believe.
Yeah.